All. In this session, I will be discussing one simple problem on spur gear. A pair of carefully cut spur gear with a 20-degree full depth envelope profile is used to transmit 12 kilowatt at 1200 rpm of pinion. The gear has to rotate at 300 rpm. The material used for both pinion and gear is medium carbon steel, whose allowable bending stress may be taken as 230 MPa. Determine the module face foot of the spur pinion and gear. Suggest suitable hardness. Take 24 teeth on pinion. Modulus of elasticity may be taken as 210 GPa. So this is the problem given where we need to determine module face width of both pinion and gear. So for this problem, we will be using the data handbook, that is Balavira Reddy of 4th edition to solve this problem. Okay, so let's go through the problem. So it has been appeared in VTU February 2002 examination. So let me write the data for this. So in the problem, he has given that 20-degree full depth involute. There is the pressure angle which is given in the problem, and the power which is 12 kilowatt, and the speed 1200 rpm, and the speed of the pinion is taken as n1. The speed of the gear is taken as 300 rpm. So here they have given in the question bending stress which is allowed for the gear, which is 230 MPa, and this is same for both pinion as well as gear member. Z1 is 24, which is given, and the modulus of elasticity is same because the materials is same for both pinion and gear, and the condition given is it is carefully cut spur gear. So this will be utilized in calculating the error factor while doing dynamic load calculation. This statement is required. Okay, let me move on to the solution part. So in this case, since n1 and n2 both are given, and also you have the value for z1, that is teeth on pinion is given as 24. So what you can do is by using gear ratio or velocity ratio formula, we can able to calculate the teeth on the gear. So n1 by n2 is equal to z2 by z1 is equal to d2 by d1. So n1 is 1200, n2 is 300. You will get the value as 4. Z2 is equal to 4 into Z1. So Z1 is 24. If you substitute that value, you will get 96. And next is, after getting the value of Z2, you can use Lewis form factor, that is calculation of Y. So Y can be calculated by using the formula Y is equal to 0.154 minus 0.912 by Z. So this is taken from the data handbook as I mentioned earlier, 204 page number 12.5D, Balved Reddy 4th edition. This I have taken. So you got this equation for 20-degree full depth involute. This is the formula. By substituting Z as Z1, you will get the value of y1 as 0.116. So let me keep it as it is. Then I will move on to next step, which is the Lewis form factor for gear y2 value. Same formula, but only thing is the substitution is z2. So z2 is 96. If you calculate, the value will be 0.1445. Once you get the y1 and y2, next you need to identify the weaker member. We need to design for the weaker member. As you know, weaker member will be failing first. So we need to design for the weaker member. As you can see, pinion and gear material are the same. So pinion will be the weaker member because the pinion size is very much less compared to gear size. As we know that torque will be different for each of the case. So here torque will be less, here torque will be more. So it has more torque. So this will fail first because of the size of the pinion, as it is a driving gear. So and it is also made of same material. Whenever same material will come, you need to choose pinion as a weaker member. So pinion will be the weaker member. Next step in design process of pinion is, first we need to calculate the tangential tooth load. So tangential tooth load, I will give it as Ft. So Ft is equal to 1000 pcs by V, where V is the velocity, meter per second, and similarly P is the power in kilowatt, and Cs is the service factor. So which I have taken from the equation 12.7a from the 4th edition data handbook Balveer Reddy, page number 205. So first we need to calculate the V value. V is nothing but the velocity, pitch line velocity. So which is given by pi d n1 by 60,000, where you will be getting the value in meter per second. As you can see, pi into d, I will write it as m into z1. So as you know, d is equal to m into z1. That is the formula. So z1 is known to you. So 24, n1 is the speed, pinion, divide by 60,000, you will get in meter per second. So it is 1.50796. That is the value. And now I will be substituting the same value in the Ft equation, 1000 P Cs divided by V. Here, very important thing is service factor. So for CS calculation, you observe that in the table 12.8 of the data handbook, page number 235, assuming that medium shock 8 to 10 hours per day, the CS, that means service factor, will come out around 1.5. This is taken from the table. Okay, so same value if I put here, you will be getting the final value as 11,937 divided by m. So after this, the next parameter, next I will be calculating Lewis equation for based on tangential tooth load. Here also I will be using Ft equation, which is sigma d, that means design stress. Cv is the velocity factor, B is the face width, Y is the Lewis form factor, and P is the pitch. So that this equation is taken from data handbook, equation number 12.5a and page number 204, where B is the face width, which I have taken it from data handbook. It will be around 9.5 to 12.5. So in between I have to take it as 10 m. M means module, and you know the equation for circular pitch, which is pi into m. which is taken from the data handbook 12.1a, page number 203, that Ft1 is equal to sigma allowable into Cv 10m y1 into pi into m. After substituting 230 Cv I don't know, 10m 0.116 pi into m. After substitution, what you can see here is that Ft1 is equal to 838.17 meter square m square into Cv. So I will take this as equation number 2. So as you can see, you got two equations, which is equation 1, which is you got it as 11,937 by m, which is also Ft value, and here also what you got is the Ft value. I will equate both the equations 1 and 2. What you get is 838.17 m square Cv is equal to 11,937 by m. After simplification, m cube, this I will transfer on the left hand side, m cube Cv is equal to 14.24. Let me put this as an equation number 3. Next, we need to do some trial and error method so that we can able to get the value of m module. So first trial method, what you can see is I will select m is equal to 3. Generally, we will start the trial from 3 mm itself in any problem in the design. So 3 mm I will select. So V is equal to C 1.50 m, 1.507 m, which I got it from here. You can able to see earlier I have calculated. Same thing I have taken here 1.507 m. M is 3, so you will get 4.521 meter per second. After getting this value, substitute that for this value 4.5. So from page number 205 in the data handbook, 12.6a equation number. So CV value comes out to be 3.05 divided by 3.05 plus V. So where V is the velocity which just we have calculated now. Just substituting that 3.05 divided by 3.05 plus 4.521. So CV value comes around to be 0.4028. So this equation is taken based on the velocity. Okay, there will be a range in which you can take the CV value based on the 4.5. The formula is this one, which you can refer from the data handbook, page number 205, equation number 12.6a. After doing that, so what you can see here from equation 3, you can see that m cube CV is equal to 14.24. I have rewritten the equation number 3. 3 cube into 0.4028 is equal to 14.24. Now, whatever value you get on the left hand side should be greater than or equal to the right hand side. Then only your module is correct. So, if I substitute m as 3, CV as 0.4028, then I got this value as 10.87, which is not greater than 14.24, which is also not equal to 14.24. So then, so that this m is equal to 3 is not suitable. So next I will go for trial number 2, where I will take m as 4 mm, and same thing I will calculate the velocity 1.507 into 4. So you will get the value as 6.028. So using 6.028, so the CV value will be from the data handbook 12.6a equation, page number 205. So the formula comes out to be this same formula. So now V I will be substituting as 6.028. So CV value is 0.33597. So after getting CV value, you observe that same thing I will do as we done in the previous case. Equation 3, m cube CV 14.24. So m is 4, CV is 0.33597. So now what I will get, the value of m cube left hand side is greater than 14.24. Then the condition is satisfied. So m is equal to 4 mm is suitable for this design. So m is equal to 4 mm is the correct value of the module. So next we will check whether the found out value is correct or not by comparing with the stress equation. So first we need to calculate allowable and induced. So induced stress has to be less compared to allowable stress. So allowable stress, the equation is very simple. We will multiply the allowable stress with CV, velocity factor. So 230 into 0.3359, just now we have calculated. Same thing I will multiply. Then you will get it as 77.257, which is allowable stress. Induced stress is nothing but which is induced on the gear. So induced is equal to sigma d into CV, which I will be using the equation from the data handbook, which I have previously used for calculating FT. FT divided by BYP. So in this case, you can see that FT1 value I will calculate first. FT1 for calculating this value. So I have in the previous case, this value I have shown in the equation 1. The same equation I have written here, 11,937 divided by m. So m is 4, you already know. Ft you got this value 2984.25. Once you got the Ft1 value, next step is to calculate induced value. Induced stress 2984.5, which is Ft, divided by, this is 10 into 4, which is your face width, and this is circular pitch, and this is the form factor. So if I substitute and if I calculate, the answer will be 51. So now you see that induced stress is very less compared to allowable stress. Hence, whatever we have calculated m is equal to 4 is suitable. The design is safe. Next step is to calculate the dynamic load. For calculating the dynamic load, what you can do is, there is a equation in data handbook, page number 207, equation number 12.12. So FD is equal to FT plus K3V CB plus FT divided by K3V plus root of CB plus FT, where FT is the tangential tooth load, and this C and B value can be taken. The C is the dynamic factor, B is the face width, and K3 also is also taken from the data handbook, which is, you can see here, 20.67. This is for SI units. It is a fixed value which I get from the data handbook below this equation. So first what we need to do is, we need to calculate the value of C, which is dynamic factor. So for calculating the C value, you need error. You need error. Why? Because in the table 12.13, page number 237, you will get the value of error. How do you get this? So based on this condition, carefully cut gears and module 4 mm, error comes out to be 0.0254. So which you get it from that table. Once you get this error, then for this error from table 12.12 and page number 236, the data handbook, for steel and steel 20 degree, and for E is equal to 0.0254, C lies between this value. This I got it from the data handbook. So it lies between this value. So I will take the average of this. So it comes out to be 285. So this is actually the C value, dynamic factor. So K3 value directly given in the data handbook, which I have entered. Then So after substitution, so Ft value is this, and this is K3 V value which I got it from 1.057 into M. So if I substitute, I will get this value. Then C is 285.95 and B is 10 into 4, 40, and this is Ft value. K3 velocity, same thing here also, CB plus Ft. So after simplification, you will get the dynamic load as 10,000. Next, we shall calculate the value of wear load. So wear load can be calculated by using this equation. Fw is equal to D1 BQK, which is taken from the data handbook 12.15A and page number 208. So here D1 is M into Z1 and B is phase width 10 into M and Q is nothing but 2Z2 by Z1 plus Z2. So after substituting all the values, so you will get in terms of K. I don't know this load factor value. So that you keep it as it is, 6144K I will get. For safer design, the wear load has to be more than this dynamic load. Wear load has to be more than this dynamic load, otherwise the design will be is not safe. For that reason, so 6144K greater than or equal to 10,328. So K value comes out to be 1.68. K value greater than or equal to this value. So for this case, now I will be calculating the BHNs, that is hardness number for each of the gear and pinion. So for calculating the hardness number, so from table 12.16, that is page number 239 of the data handbook, and for K greater than 1.68 239, and for steel and steel 20 degree, so K comes out to be more than this, comes out to be 1.893. This is from the data handbook which I have taken, and the sigma ES which I got for that K value is 892.5, which is the endurance factor, and the pinion BHN from that same table 12.16 is 350 BHN, and for gear which is also 350 BHN. So what we done in this problem is we have calculated the finally the hardness number, and also we designed completely the spur gear for the same material, that is carbon steel. So this is how you can able to do the problem on gears. So generally the material can be different. In that case, whenever the materials of the gear and pinion are different, you need to equate the equation and you need to see that whichever is weaker will have to be designed. So whenever you have case like this, material is same, then obviously make sure that whichever having less stress, that will be weaker member. When both the materials are same, and both the materials are same, pinion and gear materials are same, then pinion will be the weaker member. If both materials are different, you should calculate sigma naught y and sigma naught y for gear and this separately. So whichever having less value, that will be the weaker member. Whichever having more value, that is a stronger member. That you need to make sure. So based on the weaker member, you will be designing the gear. I hope you have understood the problem. Thank you for watching.